Subscribe to the channel so you don't miss out on any of these videos. Imagine a place in space where objects can just stay put. They don't drift away, they don't fall, and they don't need a rocket constantly pushing them to stay in one spot. Sounds like something out of science fiction, doesn't it? But here's the twist, it's entirely real. These places exist, and they're called Lagrange points. These gravitational sweet spots are not only fascinating, but they've also become some of the most strategically important locations for scientific exploration, satellite positioning, and even futuristic space colonies. What's so special about them, and why do they matter? To understand Lagrange points, we need to dive into the invisible yet incredibly powerful forces that govern space, gravity, and motion. Once you grasp how these forces interact to create these peculiar zones of balance, you'll see why they are considered one of the universe's most intriguing phenomena. Lagrange points might not grab headlines like black holes or alien planets, but they play a role in shaping our understanding of space and its dynamics. If you've ever wondered how satellites can stay in seemingly perfect orbits, or how humanity might one day build platforms for deep space travel, Lagrange points are the answer. These points aren't just theoretical curiosities. They are practical, functional, and deeply mysterious in their own way. Let's start with the basics. Space isn't just an empty void where objects float freely. Every object with mass creates a gravitational pull, and this pull is stronger the closer you are to the object. Now, imagine two massive bodies in space, like the Earth and the Sun. Their gravitational pulls tug at each other constantly. Somewhere between them, or even beyond them, there are spots where their gravitational forces and the centrifugal force caused by their orbits balance out perfectly. These are the Lagrange points. At these points, an object can effectively hover without being pulled toward one body or the other. What's fascinating is that there aren't just one or two of these points. Between any two orbiting bodies, there are 5 Lagrange points, each with its own unique characteristics. They're labeled L1 through L5, and while they share the same underlying principles, they serve vastly different purposes. L1, for instance, is located between the two bodies. Imagine placing a satellite between the Earth and the Sun, just close enough to Earth that it remains in a stable position. This point is incredibly useful for solar observation because it provides an uninterrupted view of the Sun. It's where the Solar and Heliospheric Observatory, SOHO, sits, constantly monitoring solar activity that could impact Earth. L2 is on the opposite side of Earth, away from the Sun. It's where telescopes like the James Webb Space Telescope are positioned. Why? Because L2 offers a stable, cool spot with a constant view of deep space, perfect for observing the distant universe without interference from the Sun's heat and light. L3 is trickier to visualize. It lies directly opposite Earth on the other side of the Sun. While it's a theoretical point of balance, it's not practical for placing satellites because we can't maintain direct communication. However, it still sparks curiosity. What if something were hidden there, perpetually out of Earth's view? L4 and L5 are perhaps the most stable and intriguing points. They form an equilateral triangle with the two primary bodies, like Earth and the Sun. These points are gravitationally sticky, meaning objects placed there tend to stay put. In our solar system, L4 and L5 are home to swarms of asteroids known as Trojan asteroids, which have been stable for billions of years. But Lagrange points aren't just a quirky gravitational trick. They are windows into the laws of physics and cosmic motion. They're a testament to the delicate dance of forces that keep the universe in balance. Understanding them has allowed us to achieve incredible technological feats, from maintaining satellites that monitor our planet to designing missions that push the boundaries of space exploration. What makes Lagrange points even more fascinating is their potential for the future. As humanity dreams of colonizing space, these points offer prime real estate. Imagine a space station at L1, constantly watching the Sun for dangerous solar flares, or at L2, serving as a gateway for missions to Mars or beyond. These points could even host fuel depots, acting as pit stops for spacecraft venturing into deep space. Of course, harnessing the potential of Lagrange points isn't without challenges. Stability varies depending on the point. L1, L2, and L3 require constant adjustments to keep objects in place, while L4 and L5 are more naturally stable. Still, the engineering hurdles are worth overcoming for the advantages these points offer. And here's a thought that might blow your mind. Lagrange points don't exist just between Earth and the Sun. Every pair of orbiting bodies in the universe has its own set of Lagrange points. The Earth and the Moon have them, and so do Jupiter and its moons, or any other celestial duo you can imagine. This means the universe is dotted with countless gravitational sweet spots, each one a potential target for exploration or a mystery waiting to be unraveled. In a way, Lagrange points challenge us to think differently about gravity and motion. They're not places you can see or touch, but their existence reshapes our understanding of space. They are proof that even in the vast emptiness of the cosmos, there are places of perfect balance, where the push and pull of forces create harmony. So, next time you look up at the night sky, remember that hidden within that infinite expanse are these incredible points of equilibrium. They're a reminder that even in the chaos of the universe, there is order, an elegant balance that allows us to dream of reaching farther than ever before. But as simple as the concept of balance may seem, the physics behind Lagrange points is anything but ordinary. Let's break it down even further. These points exist because of the interplay between gravitational forces and the centrifugal force that arises from the orbiting motion of celestial bodies. The mathematics behind this balance was first formalized in the 18th century by Joseph Louis Lagrange, a mathematician whose work fundamentally changed the way we understand orbital mechanics. Lagrange's breakthrough was realizing that in a system with two large masses, like the Earth and the Sun, there are points where the gravitational pull of the two bodies is exactly counterbalanced by the centrifugal force acting on a smaller object, such as a satellite. In simpler terms, it's like finding a spot in a tug-of-war where the pull is equal on both sides, allowing you to stand still without being dragged in either direction. This is why an object placed at a Lagrange point can effectively hover relative to the two larger bodies. However, the balance at these points isn't always perfect. For example, L1, L2, and L3 are known as unstable equilibrium points. This means that while an object can remain there, even a slight nudge could push it out of position, requiring constant corrections to stay on track. This is why spacecraft stationed at these points, like the James Webb Space Telescope at L2, need small, periodic adjustments called station-keeping maneuvers to maintain their position. In contrast, L4 and L5 are considered stable equilibrium points. These are like the bottoms of gravitational wells. Objects placed here tend to stay put even if they're disturbed slightly. The stability of L4 and L5 is due to the combined effect of gravity and the Coriolis force, which creates a sort of natural, gravitational pocket, where objects are gently nudged back into place if they drift. This is why L4 and L5 are home to Trojan asteroids in many planetary systems, including our own. Speaking of Trojan asteroids, their discovery is a testament to the predictive power of science. Long before these asteroids were observed, scientists predicted their existence based on the physics of Lagrange points. Today, we know that Jupiter's L4 and L5 points harbor thousands of these asteroids, which have remained in stable orbits for billions of years. These objects are like cosmic fossils, preserving clues about the early solar system. Now let's zoom in on the Lagrange points of the Earth-Sun system, as these are some of the most actively utilized and studied. The L1 point, located about 1.5 million kilometers from Earth in the direction of the Sun, is a prime spot for solar observation. Satellites like SOHO and the Deep Space Climate Observatory, SCOVR, are stationed here, giving us real-time data on solar activity and space weather. This information is critical for predicting solar storms that could disrupt power grids, satellites, and communications on Earth. The L2 point, located on the opposite side of Earth from the Sun, has become a hub for astronomical research. At L2, a spacecraft is shielded from the Sun's heat and light, providing an ideal environment for telescopes like the James Webb Space Telescope to observe faint, distant objects in the universe. The location also allows these instruments to have a stable thermal environment, which is crucial for their sensitive equipment. The L3 point, while less practical for current use, has an almost mythical allure. Situated directly behind the Sun from Earth's perspective, it's perpetually hidden from view. While we know there's nothing significant there now, the idea of a hidden object, or even a counter-Earth, lurking at L3 has been a popular theme in science fiction. L4 and L5, meanwhile, offer intriguing possibilities for the future. Their natural stability makes them ideal candidates for long-term space missions or even permanent installations. Scientists and engineers have proposed placing space habitats, research stations, or even mining operations at these points. Imagine a massive space station at L4 or L5, serving as a hub for interplanetary travel or as a platform for studying the Sun, Earth, and outer planets. But the potential of Lagrange points doesn't stop with our own solar system. Every pair of orbiting celestial bodies has its own set of Lagrange points, and these could become critical for future exploration. For example, the Lagrange points of the Earth-Moon system could serve as stepping stones for lunar exploration or as staging areas for missions to Mars. Similarly, the Lagrange points of Jupiter and its moons could provide stable platforms for studying the gas giant and its diverse system of satellites. And let's not forget the possibilities for harnessing Lagrange points in the context of space resource utilization. Asteroids and other small bodies that naturally accumulate at these points could be mined for valuable materials, providing the raw resources needed for building and sustaining human activities in space. This could help make space exploration more sustainable and less dependent on costly launches from Earth. Of course, there are challenges to overcome. While Lagrange points are useful, they're not perfect. Maintaining a spacecraft at L1, L2, or L3 requires fuel for station keeping, and even the stability of L4 and L5 can be affected by gravitational interactions with other bodies. Additionally, the distances involved, millions of kilometers in some cases, pose logistical challenges for communication, navigation, and resupply. But these challenges are not insurmountable, and the benefits far outweigh the obstacles. As our understanding of Lagrange points deepens and our technological capabilities improve, these gravitational sweet spots will likely play an increasingly central role in humanity's expansion into space. The story of Lagrange points is one of discovery, innovation, and the boundless potential of human ingenuity. From the mathematical insights of Joseph Louis Lagrange to the cutting-edge missions of today, these points have captured our imagination and advanced our understanding of the universe. They remind us that even in the vastness of space, there are places of perfect harmony, waiting to be explored. The exploration of Lagrange points is more than just a technical or scientific pursuit. It's a testament to the ways humanity can harness the natural forces of the universe. These gravitational sweet spots offer unparalleled opportunities for scientific discovery, technological advancement, and even the potential for extraterrestrial habitation. Let's delve deeper into their role in scientific discovery. Lagrange points, particularly L1 and L2, have become central to some of the most ambitious astronomical missions ever undertaken. These points allow spacecraft to maintain stable positions, avoiding the frequent orbital corrections required in other configurations. This stability is critical for long-term observational missions, which need uninterrupted, precise measurements to collect meaningful data. Take the James Webb Space Telescope, JWST, as an example. Positioned at L2, the telescope benefits from being shielded from the Sun, Earth, and Moon simultaneously, creating an environment of minimal thermal interference. This location allows JWST to maintain a constant temperature, crucial for its infrared observations. Without Lagrange points, designing such a stable observational platform would be significantly more challenging and costly. In addition to stability, the positioning of these points provides unique vantage points for studying various cosmic phenomena. At L1, satellites can continuously monitor the Sun without the interruptions caused by Earth's rotation or orbit. This uninterrupted line of sight is invaluable for studying solar flares, coronal mass ejections, and other solar activities that have direct impacts on Earth's space weather. The ability to monitor these events in real time has profound implications for protecting satellites, power grids, and even human lives from the effects of severe space weather. Beyond Earth, Lagrange points have enormous potential for advancing planetary science. Consider the Jupiter-Trojan asteroids at Jupiter's L4 and L5 points. These celestial objects are thought to be remnants from the early solar system, preserved in their orbits for billions of years. Studying them could provide invaluable insights into the conditions and processes that shape the planets and other bodies in our solar system. NASA's upcoming Lucy mission is a prime example of leveraging Lagrange points for exploration. Scheduled to visit multiple Trojan asteroids, Lucy aims to unlock secrets about the building blocks of our solar system. Missions like these highlight how Lagrange points serve as natural laboratories, offering access to objects and regions that are otherwise difficult to reach. Now let's shift our focus to the future and the possibilities that Lagrange points hold for human expansion into space. Imagine a network of space stations positioned at these points, serving as hubs for interplanetary travel, research, and resource extraction. L1 could host platforms for solar power generation, capturing and transmitting energy back to Earth. L2 could become a base for deep space telescopes, free from the interference of Earth's atmosphere and light pollution. The stable nature of L4 and L5 makes them especially promising for long-term infrastructure. These points could support large-scale habitats, protected from major gravitational disruptions. Such habitats could serve as way stations for missions to the outer planets, or even as self-sustaining colonies for future spacefarers. The potential for creating thriving communities at Lagrange points isn't as far-fetched as it once seemed, thanks to advancements in life support systems, 3D printing technologies, and renewable energy. Another intriguing prospect is the potential for mining resources at Lagrange points. Natural accumulations of asteroids at L4 and L5 could provide abundant materials for construction, fuel, and even life support. Mining these resources locally would reduce the need for transporting materials from Earth, drastically lowering the cost and environmental impact of space exploration. However, realizing these visions isn't without challenges. One of the most significant hurdles is the sheer distance and isolation of these points. Communication delays, logistical constraints, and the psychological effects of isolation are all critical issues that need addressing. Moreover, the development of autonomous systems and AI will likely play a crucial role in maintaining infrastructure and conducting operations at these remote locations. Another challenge lies in the competition for these prime cosmic real estates. As space exploration becomes increasingly commercialized, the potential for disputes over the use of Lagrange points could arise. Establishing international agreements and frameworks for the fair and sustainable use of these points will be essential for avoiding conflicts and ensuring their benefits are shared. Despite these challenges, the allure of Lagrange points remains strong. Their unique combination of stability, accessibility, and scientific potential makes them ideal stepping stones for humanity's journey into the cosmos. Whether we're observing distant galaxies, studying the Sun, or establishing a foothold for future exploration, these gravitational sweet spots will continue to play a pivotal role in our quest to understand and expand our presence in the universe. The legacy of Joseph Louis Lagrange, who first theorized these points, lives on in every mission, discovery, and innovation associated with them. His work reminds us of the profound impact that theoretical science can have on practical applications, bridging the gap between abstract mathematics and tangible progress. As we look to the future, the story of Lagrange points is far from over. Each new mission and discovery adds another chapter, bringing us closer to unraveling the mysteries of these gravitational marvels. They represent the perfect blend of nature's elegance and human ingenuity, offering a glimpse into the boundless possibilities of the universe. The role of Lagrange points in future space endeavors cannot be overstated. They stand as cosmic gateways, not only to scientific exploration but also to practical advancements in humanity's quest to reach the stars. These gravitational sweet spots have become a focal point for innovation, pushing the boundaries of what we understand and what we can achieve in space. One of the most fascinating aspects of Lagrange points is their potential as locations for advanced space observatories. Imagine telescopes capable of peering deeper into the cosmos than ever before, stationed at L2, where the thermal and gravitational stability enhances their performance. Such observatories could unlock answers to some of the most profound questions about the universe. What lies beyond the observable universe? Are there other dimensions? What exactly is dark matter, and how does it shape our cosmic neighborhood? The placement of advanced instruments at L2 isn't merely about convenience, it's about necessity. Traditional ground-based observatories are limited by atmospheric interference, light pollution, and the planet's rotational cycle. Space-based telescopes avoid these challenges, but the choice of orbit significantly impacts their capabilities. L2, in particular, offers an unobstructed view of deep space, free from the distortions caused by the Earth's proximity. This unique vantage point allows astronomers to collect data with unparalleled clarity and precision. The data collected from these missions do more than enhance our scientific understanding. They inspire new technologies and innovations. For example, the precision optics developed for space telescopes have applications in medical imaging and industrial manufacturing. The need for efficient, lightweight materials in space exploration has driven advancements in materials science, leading to innovations that benefit industries on Earth. Lagrange points also present unique opportunities for planetary defense. In the event of a potential asteroid impact, early detection is crucial. Spacecraft positioned at L1, for instance, could serve as sentinels, monitoring for incoming objects and providing advanced warning systems. These points could even host deflection systems designed to alter the trajectory of hazardous asteroids, protecting Earth from catastrophic impacts. By leveraging the stability and strategic positioning of Lagrange points, humanity could create a robust planetary defense network, ensuring our survival against cosmic threats. On a more visionary note, Lagrange points could one day serve as the hubs for interstellar exploration. As humanity considers the possibility of traveling to nearby star systems, these gravitational anchors could provide critical waypoints for assembling, fueling, and launching interstellar spacecraft. The logistics of such missions are daunting, but the potential benefits are immense. Establishing infrastructure at Lagrange points would create a foundation for exploring exoplanets, studying interstellar phenomena, and perhaps even discovering extraterrestrial life. The concept of space habitats at Lagrange points is another tantalizing possibility. Such habitats could serve multiple purposes, from research and manufacturing to tourism and colonization. Their stability reduces the need for constant station keeping, making them ideal for long-term habitation. Imagine a network of interconnected habitats, each serving as a node in a vast, space-based civilization. These habitats could rely on solar energy, mining resources from nearby asteroids, and recycling waste to create self-sustaining ecosystems. The potential for utilizing Lagrange points for resource extraction also cannot be ignored. Asteroids trapped at these points are rich in metals like nickel, iron, and platinum, as well as volatile compounds like water ice, which can be used for life support and fuel. Mining these resources locally would eliminate the high costs and risks associated with launching materials from Earth. This could spark a new space economy, where Lagrange points become bustling hubs of commerce and innovation. However, the exploitation of these resources must be balanced with considerations of sustainability and ethics. As with any frontier, the potential for overexploitation and conflict is significant. International cooperation and governance will be critical to ensure that the benefits of Lagrange points are shared equitably and responsibly. Treaties and agreements, similar to those governing Antarctica, could serve as models for managing these celestial crossroads. Beyond the practical applications, Lagrange points also offer philosophical and existential insights. Their existence is a reminder of the intricate balance that governs the universe. The interplay of gravitational forces creating these points reflects the interconnectedness of all things, from the smallest particles to the largest cosmic structures. Exploring these points challenges us to think about our place in the cosmos and the forces that shape our existence. This interconnectedness also highlights the importance of collaboration in space exploration. No single nation or organization can fully realize the potential of Lagrange points alone. International partnerships, like those that created the International Space Station, will be essential for developing the infrastructure, technologies, and expertise needed to harness these gravitational sweet spots. The challenges of working at Lagrange points are significant but not insurmountable. Advanced propulsion systems, autonomous technologies, and robust communication networks will be required to operate effectively at these remote locations. The development of these systems will not only benefit missions at Lagrange points but also pave the way for exploring even more distant regions of space. As we continue to push the boundaries of exploration, the lessons learned from Lagrange points will have ripple effects across all aspects of space science and technology. These points serve as a reminder that even in the vastness of space, there are places of balance and stability, places where the forces of nature align to create opportunities for discovery and growth. The story of Lagrange points is a testament to human curiosity and ingenuity. From the theoretical musings of Joseph Louis Lagrange to the cutting-edge missions of today, these gravitational sweet spots have captured our imagination and propelled us toward the stars. They are a symbol of what we can achieve when we dare to look beyond our horizons and embrace the unknown. The journey to understanding and utilizing Lagrange points is far from over. With each new mission and discovery, we take another step closer to unlocking their full potential. As we stand on the cusp of a new era in space exploration, these points serve as a beacon of possibility, guiding us toward a future where the mysteries of the universe are within our grasp. The profound significance of Lagrange points extends to their role as strategic stepping stones in humanity's gradual expansion into the cosmos. These gravitational sweet spots, scattered throughout our solar system and beyond, represent opportunities to establish outposts that bridge the gap between planetary surfaces and interplanetary space. Their unique gravitational characteristics offer not only stability but also a cost-effective foundation for staging missions, enabling the construction of complex infrastructures that would otherwise be prohibitively challenging to achieve in free space or on planetary bodies. Consider the prospect of using Lagrange points as construction sites for large-scale interplanetary spacecraft. Building such massive structures in the microgravity of these points would simplify engineering challenges that arise from working in stronger gravitational fields or under the limitations of a planet's atmosphere. Additionally, these points could serve as depots where spacecraft refuel and resupply, dramatically extending the reach of exploratory missions. By leveraging resources from nearby asteroids or even comets, these depots could become self-sufficient, enabling continuous operations far from Earth. Lagrange points could also become focal points for robotic exploration. Automated systems stationed at these locations could explore nearby celestial bodies, collect samples, and transmit data back to Earth. For example, L2 could house a fleet of robotic explorers designed to study the Moon's far side or the Earth-Sun system's heliosphere. These robots could be remotely controlled or operate autonomously, using artificial intelligence to adapt to unforeseen challenges. Over time, the knowledge gained from these missions would feed into larger-scale human endeavors, paving the way for manned missions to more distant destinations. As technology advances, the idea of constructing entire megastructures at Lagrange points becomes increasingly plausible. Imagine a massive ring station at L1, constantly bathed in sunlight, serving as a hub for energy generation. Solar power collected at such a station could be transmitted wirelessly to Earth or other space habitats, providing a sustainable energy source. Alternatively, these megastructures could serve as habitats themselves, housing thousands or even millions of people. Life in such habitats would require innovations in closed-loop life support systems, artificial gravity, and radiation shielding, technologies that would have transformative impacts on life on Earth as well. The potential for space tourism at Lagrange points is another avenue worth exploring. These locations offer unparalleled views of celestial phenomena, from the shimmering auroras of Earth to the swirling storms of Jupiter. A luxury space station at L1 or L2 could attract visitors seeking the ultimate travel experience, combining the thrill of zero gravity with the awe-inspiring beauty of space. While such ventures are still in the realm of science fiction, the rapid advancements in commercial spaceflight suggest that they may one day become a reality. Despite these exciting possibilities, the utilization of Lagrange points comes with its own set of challenges. One of the most significant is the threat posed by space debris. While these points are stable, they are not immune to the accumulation of debris from failed missions, discarded satellites, and natural micrometeorites. The development of debris management systems will be critical to ensuring the safety and longevity of operations at these locations. Technologies such as space tugs for debris removal or self-cleaning mechanisms for spacecraft will play a vital role in addressing this issue. Another challenge is the need for reliable communication systems. Because Lagrange points can be located millions of kilometers from Earth, maintaining a steady line of communication is no small feat. Delays and signal degradation are inherent to such distances, requiring advanced solutions like laser-based communication systems or relay satellites positioned strategically to bridge the gap. These innovations could also have applications on Earth, improving global communication networks and enabling new capabilities in remote sensing and data transmission. The exploration of Lagrange points also necessitates advancements in propulsion technology. Traditional chemical rockets are effective for initial launches but are not efficient for sustained operations in deep space. Alternative propulsion methods, such as ion thrusters, solar sails, or nuclear-powered engines, will be essential for reaching and maintaining positions at these points. Each of these technologies offers distinct advantages, from the high efficiency of ion thrusters to the virtually unlimited energy supply of solar sails. As these technologies mature, they will unlock new possibilities for exploration and utilization of Lagrange points. Beyond their practical applications, Lagrange points serve as natural laboratories for studying fundamental physics. The unique gravitational environment of these points allows scientists to conduct experiments that are impossible on Earth. For example, researchers could study the behavior of fluids, materials, and biological systems in microgravity, gaining insights that could lead to breakthroughs in medicine, engineering, and even agriculture. The ability to manipulate gravitational forces at these points also opens the door to experiments in gravitational wave detection and quantum mechanics, pushing the boundaries of our understanding of the universe. The philosophical implications of Lagrange points are equally profound. They remind us of the delicate balance that exists in nature, a balance that, when understood and harnessed, can lead to extraordinary achievements. They challenge us to think beyond the confines of our planet, to consider the interconnectedness of celestial bodies, and to embrace the potential of a future where humanity thrives not just on Earth but throughout the solar system. As we look to the future, the role of Lagrange points in our cosmic journey will undoubtedly expand. They represent a convergence of science, technology, and imagination, a place where the forces of nature align to create opportunities for exploration, innovation, and discovery. The journey to fully understanding and utilizing these points is just beginning, but the possibilities are as vast as the universe itself. From their initial discovery to their current applications and future potential, Lagrange points embody the spirit of exploration. They are a testament to human ingenuity, a symbol of our desire to understand the universe, and a beacon of hope for what we can achieve when we dare to dream. As we continue to venture into the unknown, these gravitational sweet spots will serve as guideposts, reminding us that even in the vastness of space, there is balance, order, and infinite possibility. The exploration of Lagrange points also highlights an essential aspect of humanity's progress: collaboration. These points are not confined to any one nation, corporation, or group. Their potential benefits transcend, making them a powerful symbol of what can be achieved through global cooperation. Many of the missions that have utilized Lagrange points, such as the James Webb Space Telescope at L2 or the proposed Deep Space Gateway near Earth-Moon L1, are international in nature, involving contributions from multiple space agencies, industries, and academic institutions. This spirit of collaboration is crucial for overcoming the challenges associated with Lagrange points. The sheer complexity of establishing long-term operations in these locations demands expertise from a diverse array of fields, including astrophysics, engineering, biology, and computer science. By pooling resources and knowledge, humanity can tackle these challenges more effectively, accelerating the pace of innovation and discovery. The lessons learned from such collaborative efforts could have ripple effects across other sectors, fostering a culture of cooperation that extends beyond space exploration. Lagrange points also present unique educational opportunities. Their discovery and utilization offer a compelling narrative for engaging students and the public in science, technology, engineering, and mathematics STEM. Programs that simulate missions to Lagrange points, such as student-designed spacecraft or robotic explorers, can inspire the next generation of scientists and engineers. Outreach efforts that highlight the science behind these points, how they work, why they matter, and what we can achieve with them, can demystify complex concepts and make space exploration more accessible to people of all ages. In addition to their scientific and technological significance, Lagrange points have cultural and artistic implications. The idea of hovering in a perfect gravitational balance evokes a sense of harmony and equilibrium that resonates deeply with human sensibilities. These points have inspired artists, writers, and filmmakers to imagine what life and civilization might look like in such unique environments. Whether through science fiction novels that depict bustling space stations at Lagrange points or visual art that captures their serene beauty, these points continue to fuel our collective imagination. The strategic importance of Lagrange points extends beyond Earth's orbit. In the future, similar points in the Sun-Jupiter system or the Sun-Saturn system could become crucial for exploring the outer planets and their moons. These locations offer vantage points for observing phenomena like Jupiter's Great Red Spot or Saturn's mysterious hexagonal storm at its North Pole. They could also serve as gateways for missions to more distant destinations, such as the Kuiper Belt, the Oort cloud, or even interstellar space. As humanity prepares to return to the Moon and venture to Mars, Lagrange points near these celestial bodies will play an increasingly pivotal role. For example, the Earth-Moon L1 point could house a relay station to facilitate communication with the lunar far side or a base for assembling and launching Mars-bound spacecraft. Similarly, the Earth-Moon L2 point could serve as a staging ground for missions to the lunar South Pole, where valuable resources like water ice are believed to exist. The potential for mining operations at Lagrange points is another intriguing prospect. While the points themselves do not contain resources, their proximity to resource-rich asteroids and other celestial bodies makes them ideal for coordinating mining activities. A base at Lagrange point 4 or 5 in the Earth-Sun system, for instance, could support robotic missions to nearby asteroids, extracting materials like water, metals, and rare minerals. These resources could then be used to support life in space, construct infrastructure, or even be transported back to Earth. Another futuristic concept is the use of Lagrange points as hubs for interstellar exploration. Advanced propulsion systems, such as those based on fusion or antimatter, could be constructed and tested at these points, free from the constraints of Earth's atmosphere and gravity. Once operational, these systems could launch probes to neighboring star systems, seeking to answer fundamental questions about the universe and our place within it. The ability to establish such advanced capabilities at Lagrange points underscores their importance as stepping stones to the stars. The exploration and utilization of Lagrange points also have implications for planetary defense. These points could host early warning systems for detecting asteroids or comets on a collision course with Earth. By positioning telescopes and sensors at strategic points like L1 or L2, we could achieve continuous monitoring of large swaths of the sky, providing critical time to develop and implement deflection strategies. In the event of an imminent threat, these points could also serve as launch sites for interception missions, leveraging their advantageous positions to minimize response times. As we delve deeper into the possibilities offered by Lagrange points, it becomes clear that they are not just points of interest but pivotal elements in the grand tapestry of space exploration. They encapsulate the essence of what makes space such a compelling frontier: the interplay of natural forces, the challenge of pushing technological boundaries, and the promise of uncovering profound truths about our universe. The journey to fully understanding and harnessing Lagrange points is one that will span decades, if not centuries. It is a journey that will require unwavering curiosity, relentless innovation, and an enduring spirit of exploration. But the rewards of this journey, scientific breakthroughs, technological advancements, and the expansion of human presence beyond Earth, are well worth the effort. Lagrange points remind us of a fundamental truth about our universe, that even in the vast emptiness of space, there are places where forces come together in perfect harmony. These gravitational sweet spots are more than just points in space. They are windows into the intricate dance of celestial bodies, offering us a glimpse of the underlying order that governs the cosmos. As we continue to explore these points, we are not just uncovering the mysteries of space, we are also discovering the boundless potential of human ingenuity and the enduring wonder of our quest to understand the universe. The exploration of Lagrange points also represents a milestone in humanity's ongoing effort to master the complexities of space travel. These gravitational sweet spots are not just scientifically fascinating, they are practical enablers of ambitious missions that would otherwise be infeasible. As we envision a future where humans live and work in space, Lagrange points may become essential to sustaining life far from Earth. They provide the ideal settings for deploying life support systems, growing food in controlled environments, and recycling resources, all critical elements for long-duration space missions. Take, for example, the concept of space habitats at Lagrange points. Such habitats could serve as permanent homes for astronauts, researchers, and even private citizens venturing into space. By being strategically located, these habitats could receive adequate solar energy while minimizing exposure to radiation from cosmic rays and solar flares. Shielding technologies developed for these habitats might later be applied to surface bases on the Moon, Mars, or beyond, making these endeavors safer and more sustainable. Lagrange points also hold promise for the burgeoning field of in-space manufacturing. Advanced manufacturing techniques, such as 3D printing, could be used to construct everything from spacecraft components to habitats, leveraging raw materials extracted from asteroids or the Moon. The microgravity conditions at these points are particularly advantageous for producing high-precision materials like fiber optics, semiconductors, and medical devices that would be difficult or impossible to manufacture on Earth. One fascinating possibility is the establishment of fuel depots at Lagrange points. By using water extracted from the Moon or asteroids, engineers could produce hydrogen and oxygen, the main components of rocket fuel, on-site. These depots would enable spacecraft to refuel mid-mission, extending their range and reducing the need to launch heavy payloads of fuel from Earth. Such a system could revolutionize space travel, making it more economical and sustainable, while also laying the groundwork for interplanetary exploration. The use of Lagrange points as observational outposts is another avenue worth exploring. Imagine a network of telescopes stationed at these points, providing an uninterrupted view of celestial phenomena. These telescopes could work in concert to study distant galaxies, monitor exoplanets for signs of life, or track the movement of potentially hazardous asteroids. The data collected from these observatories could transform our understanding of the universe, yielding discoveries that reshape our view of reality. Moreover, Lagrange points could play a critical role in communication. With increasing human activity in space, the demand for robust communication networks will grow exponentially. Satellites placed at Lagrange points can act as relay stations, ensuring seamless communication between Earth, spacecraft, and other celestial destinations. This capability will be particularly crucial for missions to the Moon and Mars, where real-time communication is essential for navigation, coordination, and safety. The strategic importance of Lagrange points also extends to their potential role in planetary stewardship. These points could host instruments designed to monitor Earth's climate, track natural disasters, and study the impact of human activity on our planet. By providing a unique vantage point, such instruments could offer unparalleled insights into the health of our biosphere, enabling more effective policies to protect our environment. As we explore these possibilities, it's worth considering the ethical implications of utilizing Lagrange points. Questions arise about who should govern these locations and how their resources should be managed. The Outer Space Treaty of 1967, which prohibits the appropriation of celestial bodies, provides a framework for ensuring that space remains a shared domain. However, the treaty may need to be updated to address the specific challenges and opportunities presented by Lagrange points. International cooperation will be essential to ensure that these points are used responsibly and equitably, benefiting all of humanity rather than a select few. In a broader sense, the exploration of Lagrange points is a testament to humanity's ingenuity and adaptability. These points challenge us to think differently about space, pushing the boundaries of what is possible. They force us to innovate, to collaborate, and to dream bigger than ever before. They remind us that even in the most complex and hostile environments, there are opportunities for growth, discovery, and progress. The story of Lagrange points is still unfolding. As new technologies emerge and our understanding of the cosmos deepens, these points will undoubtedly play an increasingly central role in our journey beyond Earth. They are not just scientific curiosities. They are gateways to a future where humanity thrives among the stars. Every step we take toward understanding and utilizing Lagrange points brings us closer to that future. Whether it's building space habitats, advancing scientific research, or enabling interplanetary exploration, these gravitational sweet spots are a cornerstone of our cosmic aspirations. They represent a perfect blend of science and imagination, logic and creativity, challenge and opportunity. As we continue to explore the mysteries of space, Lagrange points stand as a reminder of the incredible potential that lies within our reach. They are a symbol of what we can achieve when we dare to look beyond the familiar, embracing the unknown with curiosity and determination. In the vast expanse of the universe, these points are a beacon of possibility, guiding us toward a future where the stars are not just a distant dream, but a tangible reality. The significance of Lagrange points lies not only in their practical applications but also in the philosophical questions they raise about humanity's place in the universe. These gravitational sweet spots represent a balance, a harmony of forces, where stability emerges from chaos. They challenge us to rethink our understanding of equilibrium, to see it not as a static state but as a dynamic interplay of influences. This insight has profound implications, both scientifically and metaphorically. For scientists, Lagrange points offer a natural laboratory to study the laws of physics in action. They are perfect for testing theories about gravitational interactions, orbital mechanics, and the delicate balance that governs celestial systems. Engineers, on the other hand, view these points as opportunities to innovate, creating technologies that leverage their unique properties. For dreamers and philosophers, however, Lagrange points symbolize the potential for harmony in a complex and often chaotic universe, a metaphor for how diverse forces can come together to create something greater than the sum of their parts. Consider, for example, the delicate dance between Earth, the Moon, and the Sun. These celestial bodies exert gravitational pulls on each other, creating a system that is both dynamic and balanced. Within this system, the Lagrange points emerge as islands of stability, demonstrating how equilibrium can arise from the interplay of competing forces. This principle extends beyond astronomy, offering insights into other fields, from ecology to economics, where balance is essential for sustainability. One of the most fascinating aspects of Lagrange points is their potential to inspire new ways of thinking about space exploration. Traditionally, space missions have been designed with a destination in mind, whether it's the surface of the Moon, the orbit of Mars, or the distant reaches of the solar system. Lagrange points, however, invite us to think differently. They are not destinations in the conventional sense but rather strategic positions that enable other missions. This shift in perspective is a reminder that exploration is not just about reaching new places. It's also about finding better ways to navigate and utilize the space between. For instance, the concept of a gateway station at Lagrange point 2, L2, is a revolutionary idea that could redefine how we approach deep space exploration. Such a station could serve as a hub for missions to the Moon, Mars, and beyond, providing a convenient stopover point where spacecraft can refuel, resupply, and undergo maintenance. By reducing the need to launch heavy payloads directly from Earth, this approach would make space travel more efficient and cost-effective, opening up new possibilities for exploration and settlement. The establishment of a gateway station at L2 also highlights the importance of collaboration in space exploration. Such a project would require the combined efforts of multiple nations, organizations, and private companies, each contributing their unique expertise and resources. This collaborative approach reflects the spirit of the Lagrange points themselves, where different forces come together to create stability. It's a powerful reminder that our greatest achievements are often the result of working together, pooling our strengths to overcome challenges and achieve common goals. Lagrange points also challenge us to think about the long-term future of humanity in space. As we look beyond the immediate goals of exploration and colonization, we must consider how to create sustainable systems that can support life indefinitely. Lagrange points offer a framework for thinking about these challenges, providing locations where resources can be gathered, habitats can be built, and ecosystems can be maintained. They are stepping stones to a future where humanity is not just surviving in space but thriving. This vision of a thriving space-faring civilization is both exciting and daunting. It raises questions about how we will manage the resources of space, who will have access to them, and how we will ensure that the benefits of exploration are shared equitably. These are not just technical challenges. They are ethical and philosophical dilemmas that will require careful thought and collaboration. The Lagrange points, with their unique combination of scientific significance and practical utility, are an ideal starting point for these discussions. As we continue to explore the potential of Lagrange points, it's worth reflecting on the broader lessons they offer. They remind us that balance is a universal principle, one that applies not just to celestial mechanics but to all aspects of life. They teach us that stability is not a given but something that must be created and maintained through careful attention to the interplay of forces. And they inspire us to look beyond the surface, to see the hidden patterns and opportunities that lie within the complexity of the universe. In many ways, the story of Lagrange points is a microcosm of the human experience. It's a story of discovery, innovation, and the search for harmony in a chaotic world. It's a testament to our ability to see beyond the immediate, to recognize the deeper principles that govern our reality. And it's a reminder that even in the vastness of space, there are places where stability and balance can be found, a beacon of hope in an ever-changing universe. The concept of Lagrange points continues to intrigue and inspire not only astronomers and engineers but also thinkers from all walks of life. These gravitational equilibrium points embody a profound interplay of forces, a phenomenon that mirrors many aspects of our own existence. In the ever-changing cosmos, they serve as fixed points, places where balance emerges from chaos. This concept is as philosophically rich as it is scientifically significant. One of the most captivating features of Lagrange points is their role as gateways to the broader universe. They remind us that exploration is not merely about reaching new destinations but also about finding efficient and ingenious ways to navigate the spaces between. This shift in perspective has the potential to revolutionize how we think about space travel and settlement. Instead of seeing exploration as a linear journey from one celestial body to another, Lagrange points encourage us to consider space as an interconnected network, a dynamic system where strategic positions enable greater possibilities. For instance, consider the potential role of Lagrange points in interstellar exploration. While humanity is still far from developing the technology needed to travel to other star systems, Lagrange points could serve as staging areas for such missions. By establishing bases at these points, we could create infrastructure that supports long-duration missions, including refueling stations, research facilities, and communication hubs. These bases could act as springboards, allowing spacecraft to venture farther into the cosmos than ever before. Moreover, the use of Lagrange points for interstellar exploration aligns with the concept of incremental progress, a principle that has guided human advancement throughout history. Instead of attempting to leap directly to the stars, we can take smaller, more manageable steps, each building on the achievements of the last. Lagrange points provide the ideal locations for these intermediary steps, enabling us to gradually expand our presence in space while developing the technologies and expertise needed for more ambitious endeavors. The strategic importance of Lagrange points also extends to planetary defense. As our understanding of near-Earth objects, NEOs, grows, so too does the need for effective strategies to mitigate potential threats. Lagrange points could play a crucial role in this effort. For example, observatories stationed at L1 or L2 could provide early warning of incoming asteroids or comets, giving us more time to respond. Additionally, spacecraft positioned at these points could be used to intercept and deflect hazardous objects, reducing the risk of catastrophic impacts. The ability to monitor and respond to potential threats from space is not just a matter of scientific curiosity, it's a critical component of planetary stewardship. By leveraging the unique properties of Lagrange points, we can enhance our ability to protect Earth and its inhabitants, ensuring a safer and more secure future for generations to come. Beyond their practical applications, Lagrange points also hold a certain poetic allure. They are places where the forces of gravity, the very fabric of the universe, come into perfect harmony. This harmony is not static but dynamic, a delicate balance that requires constant interaction and adjustment. In this sense, Lagrange points can be seen as a metaphor for the human condition. Just as these points represent a balance of celestial forces, so too does our existence require a balance of competing influences: science and art, logic and emotion, individuality and community. The philosophical implications of Lagrange points extend even further when we consider their role in the broader context of the universe. They are a reminder that even in the vastness of space, there are pockets of order, places where stability can emerge from chaos. This principle resonates deeply with our understanding of life itself. Like Lagrange points, life is a delicate balance, a dynamic system that thrives at the edge of chaos, constantly adapting and evolving in response to changing conditions. As we continue to study and utilize Lagrange points, we are not just advancing our understanding of the cosmos, we are also deepening our appreciation for the principles that govern it. These points challenge us to think in new ways, to see the interconnectedness of all things, and to recognize the beauty and complexity of the universe. They are a testament to the power of curiosity and the human spirit, reminding us that even in the most challenging environments, there is potential for discovery and growth. The story of Lagrange points is far from over. As technology advances and our ambitions grow, these gravitational sweet spots will undoubtedly play an even greater role in shaping the future of space exploration. They are not just scientific curiosities. They are keys to unlocking the mysteries of the universe, stepping stones to a future where humanity thrives among the stars. In many ways, the exploration of Lagrange points encapsulates the essence of what it means to be human. It is a journey of discovery, driven by curiosity and a desire to understand the world around us. It is a testament to our ability to see beyond the immediate, to imagine new possibilities, and to work together to achieve them. And it is a reminder that even in the face of the unknown, we have the capacity to find balance, to create stability, and to move forward with hope and determination. The exploration of Lagrange points offers profound insights into the synergy of natural forces, technological innovation, and human ingenuity. These gravitationally balanced positions in space represent much more than just mathematical curiosities. They are cornerstones for humanity's future in the cosmos. By leveraging these unique regions, we not only optimize our ability to observe the universe but also establish critical infrastructure for exploration, defense, and sustainability. One of the fascinating concepts tied to Lagrange points is their potential for resource utilization. The idea of space mining has long captivated scientists and visionaries, and Lagrange points could serve as collection hubs for mined materials. Asteroids often pass through or near these regions, and some could even be parked there intentionally using advanced propulsion techniques. This approach would allow for easier processing of materials like rare metals, water ice, and other resources essential for sustaining life and fueling space missions. A Lagrange point mining operation could one day enable the construction of massive orbital structures or even interstellar spacecraft, bypassing the immense costs of launching these resources from Earth's surface. But Lagrange points are not just ideal for mining. They also hold promise for revolutionizing our understanding of the universe itself. At these positions, telescopes can observe the cosmos without interference from Earth's atmosphere or magnetic field, while maintaining a consistent vantage point. For example, at L2, telescopes like the James Webb Space Telescope, JWST, benefit from minimal thermal and gravitational interference, allowing them to peer deeper into space and further back in time than ever before. With future advancements, observatories at these points might detect Earth-like planets orbiting distant stars or uncover clues about the nature of dark matter and dark energy. Another remarkable opportunity presented by Lagrange points lies in their potential role in building a sustainable human presence in space. A station or colony established at a Lagrange point would experience relatively stable conditions, reducing the energy required to maintain its position. Such a facility could house astronauts, scientists, and engineers working on cutting-edge research, space exploration, or planetary defense projects. Furthermore, the relative proximity of Lagrange points to Earth and other celestial bodies makes them ideal for logistics hubs, where resources and personnel can be efficiently transferred between missions. For instance, a base at the Earth-Moon L1 point could serve as a launch pad for lunar exploration. Similarly, a station at L2 could support missions to the far side of the Moon, where a permanent lunar observatory could be established, shielded from Earth's radio noise. This interconnectivity could form the backbone of a thriving space economy, with Lagrange points acting as pivotal nodes in a network that spans the solar system. In addition to their practical applications, Lagrange points raise profound scientific and philosophical questions. For example, the stability of these points, where gravitational and centrifugal forces perfectly balance, mirrors concepts found in fields as diverse as quantum mechanics, economics, and ecology. In quantum physics, for instance, there are parallels in the way particles find points of equilibrium within potential wells. Economically, Lagrange points symbolize markets that achieve a dynamic balance between supply and demand. Ecologically, they echo the delicate equilibrium seen in sustainable ecosystems. These cross-disciplinary parallels suggest that the study of Lagrange points could inspire breakthroughs in entirely unrelated fields. Yet, with all their promise, Lagrange points also present challenges. Their stability is often conditional rather than absolute, meaning that objects placed there may require occasional course corrections to maintain their position. This phenomenon, known as quasi-stability, occurs because gravitational forces at these points are sensitive to external influences, such as the gravitational pull of nearby celestial bodies or solar radiation pressure. Designing systems to operate effectively in such environments will require precise engineering, robust control algorithms, and an understanding of the long-term dynamics of these regions. Moreover, as humanity continues to utilize Lagrange points, ethical considerations will inevitably arise. Who will have the right to claim and exploit these regions? Will they be governed by international treaties, or will they become contested territories, like the early days of terrestrial exploration? As with all frontiers, the use of Lagrange points will require careful planning, cooperation, and a commitment to ensuring that their benefits are shared equitably. Despite these challenges, the potential of Lagrange points remains boundless. They are, quite literally, the gravitational crossroads of our solar system, a nexus where science, technology, and human ambition converge. From enabling groundbreaking discoveries to serving as platforms for interstellar exploration, they are key to unlocking the next chapter of humanity's journey into the cosmos. Looking further ahead, Lagrange points might even play a role in solving some of humanity's most pressing existential challenges. Climate change, for example, could potentially be mitigated using solar shields or mirrors placed at L1, where they could reflect or absorb sunlight to regulate Earth's temperature. While such ideas are currently speculative, they illustrate the vast range of possibilities that Lagrange points offer for addressing global challenges. As we continue to explore and innovate, it's important to recognize that Lagrange points are not just abstract concepts or distant locations. They are a testament to the power of human imagination and our ability to find order in the seemingly chaotic. They remind us that the universe is not merely a collection of isolated objects but a dynamic, interconnected system governed by fundamental principles of balance and harmony. Ultimately, the study and utilization of Lagrange points exemplify the best of what humanity can achieve when curiosity meets creativity. They invite us to dream big, to push the boundaries of what is possible, and to envision a future where the cosmos is not just a frontier to be explored but a home to be shared. In their simplicity and elegance, these gravitational sweet spots offer a profound lesson. Even in the vastness of space, balance is the key to unlocking infinite potential. As we move further into the age of space exploration, the strategic value of Lagrange points will only increase. The technological leaps that humanity has made in recent decades, particularly in the realms of propulsion systems, robotics, and artificial intelligence, have made the idea of harnessing Lagrange points for a variety of purposes more feasible than ever before. We can envision a future where these gravitational sweet spots are not just passive observatories, but active hubs for deep space missions, scientific research, and even resource extraction. One of the most compelling aspects of Lagrange points is their capacity to serve as staging grounds for missions to other parts of our solar system and beyond. The Lagrange points that lie between Earth and the Moon, or Earth and the Sun, could be used as points for interplanetary rendezvous. For instance, a spacecraft launching to Mars or Venus might first pass through the Earth-Moon L1 point to conduct necessary repairs, resupply, or change course. Such locations act as waypoints in the journey to distant planets, ensuring the sustainability of long-duration missions while minimizing the need for fuel and resources from Earth. This strategic positioning of Lagrange points opens up new opportunities for collaborative efforts in space exploration. By establishing multiple space stations and colonies across different Lagrange points, we can create a network of interconnected outposts. These stations could function as research hubs, fueling the development of advanced technologies such as next-generation propulsion systems, autonomous spacecraft, and more efficient energy sources. If these outposts are positioned effectively, they could also serve as safe havens for astronauts traveling across the solar system, providing them with places to rest, resupply, and replan their missions before continuing their journey. Another major advantage of Lagrange points is their potential use in deep space communication. The placement of satellites and communication relays at these points could greatly improve the speed and efficiency of data transmission across vast distances. For example, sending a signal from Earth to a spacecraft traveling to the outer reaches of the solar system takes a considerable amount of time due to the vast distance involved. But with a network of relay satellites stationed at various Lagrange points, these signals could be bounced and sent back and forth at higher speeds, making real-time communication with distant spacecraft more feasible. One area where Lagrange points could drastically change the future of space exploration is in the study of exoplanets. By positioning observatories at Lagrange points, astronomers would have an unobstructed, steady view of distant star systems, allowing them to detect faint signals from exoplanets that might otherwise go unnoticed. These Lagrange point telescopes could help identify planets in the habitable zone of other stars, those regions where life-sustaining conditions might exist, and perhaps even study the atmospheres of these worlds in greater detail. This could give us our first real chance to explore the possibility of extraterrestrial life beyond our own solar system. Furthermore, the study of asteroids and comets could be revolutionized through missions that capitalize on Lagrange points. The placement of observatories or robotic spacecraft at these gravitationally stable locations would allow for precise tracking of these celestial bodies, which might be rich in water, metals, or other valuable resources. Asteroid mining, though still in its infancy, has the potential to provide raw materials for space-based industries, including the construction of massive space habitats, solar arrays, and other large-scale space infrastructure. By monitoring these asteroids from a stable Lagrange point location, missions could be planned with unprecedented accuracy, improving the efficiency of resource extraction efforts. One of the more visionary concepts associated with Lagrange points is their potential to act as stepping stones for the colonization of space. While building self-sustaining colonies on other planets is still far from a reality, the strategic placement of habitats at Lagrange points could provide a critical first step in the development of a permanent human presence in space. These colonies could be used for research, manufacturing, or as way stations for missions destined for the Moon, Mars, or beyond. With the perfect balance of gravity and minimal fuel requirements, these colonies could serve as launch points for future space missions, drastically reducing the costs of traveling deeper into the solar system. Yet the implications of utilizing Lagrange points are not solely limited to technological advancements or economic opportunities. They also offer profound insights into how we might think about the future of our species and our place in the universe. As we continue to explore these gravitational sweet spots, we might begin to appreciate how interconnected we are with the forces that shape our environment. These points serve as metaphors for the delicate balance required to sustain life, both on Earth and in space, and remind us of our responsibility to care for the world we call home. In addition, as we position more technology at these points, the ethical questions surrounding space exploration will become even more pronounced. Who owns these strategic locations in space? Should they be governed by international law, and if so, how will that law be enforced? While the Outer Space Treaty of 1967 established the principle that space is the province of all mankind, these questions will likely become more complex as space exploration progresses. The more humanity explores and exploits these regions, the more we'll need to develop frameworks that ensure peaceful cooperation and equitable access to the resources and opportunities that Lagrange points present. One of the more intriguing aspects of Lagrange points is the sense of permanence they convey. Unlike Earth, which is subject to the dynamic forces of tectonics, weather, and natural disasters, the points in space remain stable over long periods of time. Their constancy offers a contrast to the fragility of life on our home planet, serving as a reminder that there are places in the universe where stability and balance can be achieved even amid the chaos of the cosmos. This may encourage a shift in how we perceive our relationship with space, less as a wilderness to be conquered and more as a vast, interconnected network in which we are but one part. As humanity prepares to take the next steps in space exploration, we are confronted not only with the challenges of technology and logistics, but also with deeper questions about our long-term goals. Lagrange points stand as a metaphor for these goals, a vision of a future where we have learned to navigate the complexities of space in a balanced, sustainable way. They invite us to look beyond our immediate concerns and consider what it means to build a future that is not just driven by scientific curiosity or economic gain, but by a profound respect for the forces that govern the universe. The story of Lagrange points is one that will continue to unfold for generations to come. These gravitational sweet spots are more than just theoretical locations. They are windows into the future of space exploration and the opportunities that await us beyond our home planet. Whether we use them to build space stations, mine asteroids, or explore distant star systems, Lagrange points will undoubtedly play a key role in shaping humanity's future among the stars. As we look deeper into the future of space exploration, Lagrange points represent more than just strategic locations for observation, research, or resource extraction. They signify humanity's potential to evolve in ways that were once unimaginable. These regions in space are not just areas of convenience for spacecraft, but critical touchpoints in our journey to not only explore the cosmos but to live and thrive within it. In the coming years, the applications of Lagrange points will extend well beyond just research and exploration. As more space missions take place, the need for space stations and orbital outposts will become a reality, and Lagrange points could provide the ideal locations for these bases. Consider the prospect of space tourism, which has already begun in the early 21st century. Space tourists may one day be able to travel to orbital hotels or stations at Lagrange points, where they can enjoy a stunning view of Earth or the Sun and the farthest reaches of the solar system. These unique vantage points would provide an unparalleled experience, offering a perspective on our planet that most people could never even dream of. And with the ongoing development of commercial space flight, it is not out of the realm of possibility to imagine that these far-flung space locations could one day be opened for the general public. Lagrange points also hold promise in solving one of the biggest challenges of space exploration: long-duration space missions. When traveling beyond Earth's orbit, maintaining the health and well-being of astronauts is paramount. Prolonged exposure to the harsh conditions of space, including radiation and microgravity, can have severe consequences on human health. However, Lagrange points offer a unique advantage in mitigating some of these risks. By establishing stations or shelters at specific Lagrange points, astronauts could rest and resupply in a relatively stable environment before continuing on their missions. The Lagrange points could provide a more comfortable and safe environment for crew members on long journeys to the Moon, Mars, or beyond, allowing for periodic resupply missions and the opportunity for rest and recovery. In addition to providing a base for astronauts traveling to distant planets, these points could play a critical role in helping humanity transition from being Earthbound to becoming an interplanetary species. It's one thing to send a probe or a satellite to Mars or beyond, but it's quite another to send humans. The challenges of sustaining human life on other planets, including producing food, water, and oxygen, are monumental. But Lagrange points could offer a middle ground. By establishing semi-permanent habitats in orbit, these locations could serve as launch points for missions to settle other worlds. Here, astronauts could undergo the necessary training, adjustments, and resupply missions before embarking on the more significant challenges of living on another planet. Moreover, the closer we get to understanding how to harness the resources of space, the more Lagrange points become essential in the process of space colonization. Space mining, which seems like science fiction, could one day be a viable industry. The asteroids that orbit the Sun in the asteroid belt or in the Oort cloud are filled with valuable minerals, metals, and even water. Lagrange points can serve as excellent locations for observing, mining, or extracting materials from these objects. The advantage here is the proximity to the stable points in space, where robotic mining operations could be set up to extract resources. These materials could then be sent back to Earth or used to build more infrastructure in space, facilitating humanity's presence in the solar system. The future of solar power might also hinge on Lagrange points. Given their unique positioning and constant exposure to sunlight, these points are ideal locations for solar energy collection. Solar power satellites stationed at Lagrange points could generate vast amounts of energy without the limitations imposed by Earth's atmosphere or night cycles. These satellites could transmit the harvested energy to Earth via microwave or laser beams, providing a constant, reliable source of energy for humanity. This idea, once considered speculative, is now under serious investigation as a potential solution to our growing energy demands. However, as promising as the future looks, the establishment of human settlements or research stations at Lagrange points doesn't come without its challenges. Despite their stability, these locations are still far from the Earth's protective atmosphere. Prolonged exposure to cosmic radiation, micrometeoroids, and the absence of an atmosphere would present significant risks. Habitats at these points would need to be equipped with advanced shielding technologies to protect inhabitants from these hazards. Additionally, the long-term effects of living in a microgravity environment on human health need to be studied in greater detail. Muscle atrophy, bone loss, and psychological challenges are all real concerns for people who might live in space for extended periods. Even as technology advances and we learn to overcome some of these obstacles, Lagrange points also present unique opportunities for future scientific breakthroughs. One area that could benefit from research at Lagrange points is the study of the Sun. The Sun plays a crucial role in the space weather that affects our planet, and understanding its activity is critical for our safety and the health of our technological infrastructure. Placing solar observatories at Lagrange points like L1 would allow scientists to study the Sun without any interference from Earth's atmosphere. These observatories could provide real-time data on solar flares, coronal mass ejections, and other phenomena that can have a direct impact on life on Earth, including satellite communications and power grids. Moreover, the study of gravitational waves, a topic that has gained a lot of attention in recent years, could also benefit from Lagrange point-based observatories. Gravitational waves are ripples in space-time caused by massive objects, such as colliding black holes or neutron stars. Detecting these waves requires incredibly sensitive instruments, and Lagrange points offer an ideal location to place observatories designed to capture these faint signals. By positioning them far from Earth, where local gravitational noise could interfere with measurements, scientists could make more accurate and meaningful discoveries about the fundamental nature of the universe. Perhaps most significantly, the exploration of Lagrange points offers us a chance to reflect on our place in the universe. These regions of space, with their perfect balance between competing forces, are a symbol of the delicate equilibrium that allows life to exist. They serve as a reminder that, while we may be small in the grand scheme of things, we have the capacity to explore, understand, and even shape the future of space exploration. By harnessing the power of Lagrange points, we might not just be taking our first steps into the cosmos, we may also be taking the first steps toward becoming a truly interplanetary species. The next decades will likely see significant progress in our understanding and use of these gravitational sweet spots. As space agencies, private companies, and international collaborations work together, the Lagrange points may very well become the launch pads for humanity's greatest adventures yet. They could provide the perfect environment for both research and colonization, and in doing so, they may unlock mysteries of space that we can't even begin to imagine today. Lagrange points are not just scientific curiosities. They are stepping stones to the future of space exploration. These gravitational, sweet spots offer a unique opportunity to unlock a deeper understanding of the cosmos, and our growing interest in them is a reflection of the changing nature of space exploration. As space technology advances, humanity's ability to establish a presence beyond Earth becomes more achievable. But to fully realize this potential, we must understand how to exploit the unique properties of these points in space. One of the key areas where Lagrange points could be of immense value is in space tourism and commercial ventures. The potential for establishing orbiting hotels, research facilities, or even artificial gravity environments in the future is high. Imagine a future where tourists could visit a luxury hotel situated at one of these points, offering them an unobstructed view of Earth or the Sun. This vision could become a reality sooner than we think, as private companies are already developing commercial spaceflight, and new space stations are being planned for low Earth orbit. The advantages of positioning these stations at Lagrange points are obvious: stability, constant exposure to sunlight, and the ability to remain relatively undisturbed by Earth's gravitational pull. Beyond leisure and tourism, commercial ventures in space could expand dramatically. From asteroid mining operations to satellite repairs, Lagrange points are strategically placed for various industries to benefit from the unique conditions they offer. For example, the ability to harvest asteroids and send resources back to Earth could become a reality if we establish mining stations at these locations. These minerals could be used for manufacturing, fueling spacecraft, or even building space infrastructure. The potential to extract materials such as rare metals or water ice from asteroids could transform how we think about resource scarcity on Earth. And all of this could be managed with minimal interference from Earth's gravity well, ensuring that such operations can be carried out efficiently and sustainably. On the subject of sustainability, Lagrange points can also serve as staging posts for sustainable energy production in space. Solar power satellites located at these points would not need to account for the interference of Earth's atmosphere or the cyclical day-night cycle. These satellites could beam power back to Earth constantly, providing a continuous energy source regardless of weather conditions. The constant supply of solar radiation at Lagrange points offers unparalleled opportunities to tap into clean, renewable energy, and could play a vital role in solving Earth's energy crisis. This concept is already being discussed by both space agencies and private enterprises, with the hope of developing the necessary technology to realize it within the next few decades. However, there are still significant challenges to overcome. The construction of such advanced space infrastructure and the establishment of permanent human settlements at Lagrange points will require new materials, advanced technologies, and robust international cooperation. Technologies in propulsion, energy storage, and construction will have to evolve rapidly to support long-term human presence in space. Habitats and other structures will need to be built to withstand the harsh environment of space, and sophisticated life support systems will need to be developed to keep astronauts safe for extended periods. Beyond technical challenges, there will be logistical hurdles to overcome, such as cost, supply chains, and ensuring the safe transport of humans and materials to these far-off locations. But despite these challenges, the strategic importance of Lagrange points cannot be understated. Whether for space observation, resource harvesting, or long-term space colonization, these regions are poised to play a critical role in humanity's future in space. Their stable positions make them ideal for the future of space exploration, offering us opportunities for unprecedented research, commercial enterprise, and even human habitation. In the longer term, the importance of Lagrange points may go beyond the mere function of observation or resource extraction. As we look further into the future, these points could serve as the hubs of a solar system-wide transportation network. Consider a scenario in which human colonies are established on the Moon or Mars. Ships traveling between planets could use Lagrange points as way stations or refueling depots. Since these points are gravitationally stable, They provide the perfect locations for ships to park while they await resupply or undergo maintenance. Even now, the idea of using Lagrange points as interplanetary transportation hubs is being discussed as part of plans for future missions to the outer planets and beyond. These hubs could also play a key role in interplanetary communication. Communication between Earth and distant spacecraft is often delayed due to the vast distances between us. But placing communication relays at Lagrange points could help streamline these systems. These points offer a stable position from which signals can be relayed between Earth and distant spacecraft or colonies, improving the efficiency of communications across the solar system. Given the inevitable expansion of our spacefaring activities, these systems will be crucial for maintaining contact with humanity's future outposts in space. The future of space exploration will increasingly rely on our ability to harness the potential of these gravitational sweet spots. Whether for research, resource extraction, or as launch points for human exploration, the significance of Lagrange points cannot be understated. The growing interest in them reflects a shift in how we view the cosmos, from something distant and inaccessible to a vast, interconnected network of potential waiting to be explored. While many of the ideas we've discussed are still in the realm of science fiction, the rapid pace of technological advancement suggests that the dream of establishing permanent human outposts in space, powered by solar energy, supported by mining operations, and connected by interplanetary transportation hubs, may not be as far off as it seems. As we venture further into the unknown, Lagrange points will be crucial in turning these possibilities into reality. We stand on the precipice of an exciting new era in space exploration, and the gravitational sweet spots scattered across the solar system could very well be the keys to unlocking humanity's future in space. The coming decades will likely be filled with groundbreaking discoveries, not just about the nature of space, but about ourselves. As we take these bold steps into the cosmos, Lagrange points will be there, providing a steady foundation for us to build on. Whether we are sending telescopes to observe distant stars, mining asteroids for resources, or launching the first interplanetary missions, these sweet spots in space will continue to guide humanity toward new horizons. And so, the journey has just begun. As we look to the future, it is clear that Lagrange points will play a central role in humanity's quest to become a true space-faring civilization. They will serve as the bridge between our home planet and the stars. And who knows? In the not-so-distant future, we may look back on these humble gravitational points as the very beginning of a new era of exploration, discovery, and perhaps even the first steps toward becoming a multiplanetary species. As we continue to dive deeper into the significance of Lagrange points, we begin to realize just how crucial they are in the future of space exploration. While we've touched on their potential for commercial ventures, resource extraction, and interplanetary communication, it's important to further expand on the potential impact of Lagrange points on the scientific exploration of space. Lagrange points, particularly those in the Earth-Sun system, offer a vantage point unlike any other. For astronomers, these points could be invaluable in the quest to study distant celestial objects. The ability to position telescopes at Lagrange points, away from the interference of Earth's atmosphere and far from the noise of its electromagnetic signals, provides astronomers with a clearer, more stable view of the universe. This could revolutionize our understanding of space, allowing us to observe stars, planets, and galaxies in unprecedented detail. One of the most famous examples of this potential is the James Webb Space Telescope, JWST. Although JWST is not situated at a Lagrange point, its location in space allows it to operate in a way that is somewhat similar to what a Lagrange point-based observatory could achieve. However, future telescopes positioned at one of these points would have an even more advantageous view of the cosmos. By using the stable gravitational equilibrium offered by the Lagrange points, scientists could send observatories that remain undisturbed for long periods of time, free from the distortions and fluctuations that often impact ground-based telescopes. This would enhance our ability to study the formation of galaxies, the behavior of supermassive black holes, and the intricate processes that govern star formation. Moreover, Lagrange points could also play a role in observing phenomena within our own solar system. Placing a probe at Lagrange points could give scientists an ideal platform from which to monitor the Sun's activity. These points could be strategically positioned to track solar flares, coronal mass ejections, and other solar phenomena in real time. Understanding the Sun's behavior is vital for protecting not only our satellite infrastructure but also future space exploration missions. The ability to observe solar activity from a stable, uninterrupted location could improve our ability to predict space weather and protect our technology from the potentially harmful effects of solar radiation. But the benefits of Lagrange points aren't limited to telescopes and scientific probes. They could also be key to expanding our understanding of how the universe operates on a fundamental level. The stable, low-gravity environment at Lagrange points could be ideal for conducting experiments that are impossible to carry out on Earth. Without the interference of gravity, scientists could study how particles behave in a microgravity environment. This could lead to breakthroughs in physics, materials science, and even biology. We could gain insight into how life may survive on other planets, or how to create more efficient systems for energy storage or manufacturing. As we look toward the possibility of human habitation at Lagrange points, we also have to think about how these points might become launch pads for deeper space exploration. The high cost of escaping Earth's gravity well means that future space missions will need all the help they can get. Lagrange points offer an ideal place to launch interplanetary missions. Ships could depart from these stable points, avoiding the gravitational drag that comes with launching directly from Earth. This could make interplanetary travel more efficient, and could reduce fuel costs for missions to Mars, the outer planets, or even distant exoplanets. Even as space technology advances, one of the main barriers to interplanetary exploration is the fuel and energy needed to launch spacecraft. This is where the concept of space-based fuel depots comes into play. Establishing a refueling station at a Lagrange point could help alleviate some of the logistical hurdles associated with long-distance space travel. Spacecraft could stock up on fuel or supplies at these points before continuing on their missions, cutting down on the weight and complexity of the spacecraft. In addition to serving as refueling stations, Lagrange points could also be hubs for manufacturing. The unique conditions at these points could make them ideal locations for producing specialized equipment or spacecraft components. As space exploration becomes more advanced, the demand for specialized materials and technologies will increase. Lagrange points could offer a stable, resource-rich environment for these operations, allowing for the construction of space infrastructure that supports further exploration. Now, let's consider the strategic importance of Lagrange points beyond just their practical uses. This raises interesting questions about the future of international cooperation and regulation in space. As commercial spaceflight becomes more prevalent, and as nations increasingly rely on space for communication, navigation, and scientific research, it will be essential to establish treaties and agreements regarding the use of Lagrange points. International cooperation will be necessary to prevent the militarization or monopolization of these critical regions, and to ensure that space remains a domain of peaceful exploration and collaboration. But space is vast, and the challenges that lie ahead are enormous. The idea of establishing permanent human outposts at Lagrange points, while feasible, presents a series of challenges that must be addressed. We've talked about the scientific and practical benefits, but now we must consider the realities of living in space. The technological, financial, and human resources required to make this vision a reality will be substantial. One of the biggest hurdles is the development of life support systems. While space stations like the International Space Station, ISS, provide a glimpse into the feasibility of living in space, the conditions at Lagrange points present unique challenges. These locations are far from Earth, which means that resupply missions would be more complex and expensive. Developing autonomous systems that can maintain life support, recycling, and energy generation will be critical to ensuring that human outposts at these points can operate sustainably. In addition, the psychological and physical challenges of living at Lagrange points would need to be addressed. Astronauts living at these locations would face extended periods of isolation from Earth, which could have significant mental health implications. Ensuring that future space pioneers have the support they need to thrive in these environments will be a key component of long-term space exploration. Scientists are already studying the effects of prolonged space travel on the human body, and understanding how the unique environment of Lagrange points might affect astronauts will be crucial. Furthermore, the engineering challenges of establishing permanent infrastructure at these locations should not be underestimated. While Lagrange points offer stable gravitational positions, they are still in a harsh and unforgiving environment. Without Earth's atmosphere to protect against cosmic radiation and solar particles, any infrastructure built at these points would need to be equipped with radiation shielding. Developing the materials and technologies necessary to protect human colonies and space infrastructure from these threats will be vital for the safety and longevity of space missions. Lagrange points represent one of the most promising frontiers in space exploration. Their unique gravitational properties offer stability, efficiency, and strategic value that make them ideal locations for a wide range of activities, from scientific research to commercial ventures, and even the future of human settlement in space. As we push further into the cosmos, these gravitational sweet spots will likely become critical hubs in the network that connects Earth with the wider universe. But as with all frontiers, the road to utilizing these points will not be without its obstacles. Technological, financial, and logistical challenges will need to be overcome. However, with continued innovation and international cooperation, Lagrange points could play a pivotal role in shaping the future of humanity's journey into space. As we continue to look up and explore the stars, these points will be there, guiding us toward new discoveries, new possibilities, and a new era of space exploration. As we venture deeper into the subject of Lagrange points, it's essential to consider the broader context of their role in humanity's vision for space exploration. What may seem like theoretical concepts on paper are rapidly transforming into practical goals, as technological advancements continue to reshape the future of space travel. These gravitational sweet spots, scattered across the vastness of space, offer a promising foundation for the next great leap into the cosmos. Understanding how they function not only opens up new possibilities but also requires us to rethink how we approach space travel, resource management, and even human settlement beyond Earth. When we talk about Lagrange points, we're discussing more than just a scientific curiosity. We're looking at locations that could become the cornerstone of humanity's ambitions in space. From a purely physical perspective, Lagrange points are fascinating in that they embody a perfect balance between the gravitational pull of two massive bodies, such as Earth and the Sun, or Earth and the Moon. At these points, objects can maintain a stable position relative to both celestial bodies without expending energy to stay in place. This remarkable feature has enormous implications for everything from space-based telescopes to potential human colonies. Now, let's expand on this idea, considering how these points could serve as springboards for future exploration. Imagine the possibilities. If we could establish permanent human outposts at these locations, these points could serve as launching pads for missions to the outer planets. The potential for fueling interplanetary travel and long-term space exploration could be exponentially enhanced. Establishing infrastructure at these points might alleviate the burden of launching massive spacecraft from Earth's surface, which requires overcoming significant gravitational forces and energy expenditures. By setting up stations at Lagrange points, we could develop a much more efficient way of reaching deeper space, potentially opening up entire sectors of the solar system for exploration. Moreover, the stability provided by these points could allow for long-term observation of celestial phenomena. While we've already mentioned the ability to observe the Sun and monitor solar activities from a Lagrange point, there is much more to consider. The capability to park telescopes or other scientific instruments at these stable positions would revolutionize our understanding of distant objects in the universe. Beyond just observing our own star, we could explore the far reaches of our galaxy, study the dynamics of distant exoplanets, and even keep an eye on the mysterious forces that govern the cosmos, such as dark matter and dark energy. Lagrange points may not just serve as observation points, but could also house facilities dedicated to conducting groundbreaking experiments that require a neutral, unperturbed environment. One area where Lagrange points could truly shine is in the field of asteroid mining. As humanity begins to look beyond Earth for resources, asteroids are considered one of the most promising targets for raw materials like metals, water, and other essential substances. Lagrange points offer a natural advantage in this regard, providing locations where mining operations could be set up with minimal interference from Earth's gravity. These points are not only stable but are strategically positioned in relation to asteroid belts and other celestial bodies, allowing for easier access to resources that might otherwise be difficult to reach. Asteroids, with their wealth of materials, offer great promise for fueling long-term space missions, especially as we consider the ambitious goal of human exploration and eventual settlement on Mars. The ability to harvest resources from asteroids and transport them back to space stations located at Lagrange points could be the key to maintaining sustainable space exploration. Moreover, this infrastructure could act as a vital hub for storing and processing resources that are crucial for future space missions. By tapping into this potential, humanity could build the foundation for a robust off-world economy that extends far beyond Earth. On a broader scale, Lagrange points could also serve as critical points for interplanetary communication. Given their strategic locations and the vast distances involved in space travel, one of the challenges of exploring the solar system lies in maintaining reliable communication links between distant spacecraft and Earth. The presence of Lagrange points, particularly those in the Earth-Sun system, could facilitate communication networks that extend far beyond our planet. These points could host relay stations, boosting signal strength and ensuring that data transmission remains uninterrupted, even for missions that venture into the outer reaches of the solar system. The placement of satellites and communication stations at Lagrange points could also help to mitigate the challenges posed by Earth's atmosphere and magnetic fields. These natural barriers can distort signals, making deep space communication a tricky proposition. But with strategically placed relay stations at Lagrange points, we could create a network that ensures constant, reliable communication, even with the most distant probes and rovers. However, the more we talk about the practical uses of Lagrange points, the more we realize that establishing permanent infrastructure in these areas would not be without its challenges. As we mentioned earlier, the technological requirements for sustaining human life at Lagrange points are immense. The stability of these locations does not make them immune to the harsh conditions of space. The absence of an atmosphere means constant exposure to cosmic radiation, and the temperature fluctuations between the sun-facing side and the shadowed side could be extreme. Creating habitats that protect against radiation and temperature swings would require significant engineering breakthroughs. Even the most advanced life support systems that have been tested aboard the ISS would need to be adapted for the specific conditions at Lagrange points. These stations would have to rely on solar energy to power their systems, which means that the technology for efficient solar panel systems will need to be taken to the next level. Energy storage, recycling of air and water, and maintaining a stable, self-sustaining ecosystem would all be crucial components of a viable human outpost at these points. Additionally, while Lagrange points provide a stable position in space, the psychological impact of living in such isolated environments cannot be overlooked. The distance from Earth, the lack of natural gravity, and the potential for long periods of solitude may pose significant challenges for those stationed at these locations. However, these challenges are not insurmountable. Advances in space medicine and psychological support, along with better mission planning and the integration of virtual reality or other immersive technologies, could help astronauts adapt to life in these unique environments. In the long term, as space travel becomes more routine, it's possible that Lagrange points could evolve from mere scientific outposts to bustling hubs of activity. Just as our planet Earth has evolved into a global network of interconnected cities and industries, the regions around Lagrange points may become the starting points for interplanetary trade, commerce, and even tourism. Space stations, research facilities, and even leisure centers could eventually spring up at these critical points in space, making them integral parts of humanity's expanding presence in the cosmos. Ultimately, the potential of Lagrange points is vast and multifaceted. While we have explored some of their most promising uses, it's clear that this is only the beginning. As we continue to innovate and push the boundaries of what's possible in space exploration, the role of Lagrange points will only grow in significance. They represent a key to unlocking the future of human space travel, resource management, scientific discovery, and beyond. As we look to the stars and imagine the possibilities of space exploration, it's important to remember that the answers to some of our most pressing questions may lie at these very points in space. With continued research, technological advancements, and collaboration across the globe, the mysteries of Lagrange points may one day be fully unlocked, providing humanity with new frontiers to explore, learn from, and inhabit. The journey ahead is long and challenging, but it is a journey that begins with understanding the gravitational sweet spots that lie just beyond our reach, waiting for us to harness their potential and take the next step into the vast unknown. As we delve even further into the future of space exploration, the role of Lagrange points is only set to grow more profound. Their potential not only extends to space stations and telescopes, but also to the possibilities they hold in making the vast stretches of space more accessible for scientific research, resource extraction, and even human habitation. The deeper we go into these concepts, the more one can imagine the complex and interconnected systems that will emerge as humanity adapts to a future where Lagrange points are no longer just theoretical, but fully operational parts of our extraterrestrial infrastructure. One intriguing concept to consider is the potential use of Lagrange points in the development of solar power satellites. These space-based power plants would essentially collect solar energy in space, where sunlight is constant and unaffected by the day-night cycle or weather patterns on Earth. This energy could then be transmitted to Earth via microwave beams or lasers, offering a renewable energy source that could help meet our planet's ever-growing demand for power. The most ideal positions for such solar power satellites would likely be at the Earth-Sun Lagrange point, where the satellite would receive uninterrupted sunlight while staying in a stable orbit. This vision could be one of the game changers of the next century. The idea of harnessing the infinite energy of the Sun, using the gravitational stability of Lagrange points to facilitate solar power transmission back to Earth, is truly revolutionary. However, it's important to note that building such infrastructure would require advancements in both space technology and energy transmission systems. The ability to capture energy from space and beam it back to Earth safely and efficiently would require cutting-edge research in fields such as wireless energy transmission and space-based construction. At the same time, Lagrange points may provide an essential role in the development of space industries that go beyond exploration and research. As Earth's resources continue to be stretched thin and the demand for metals, water, and energy increases, mining operations on asteroids and moons may become one of the most vital sources of materials for our future. The notion of asteroid mining is not a new one, but using Lagrange points as bases or relay stations for such operations could make it far more feasible. Asteroids are rich in valuable materials such as platinum, gold, iron, and water, the latter being an essential resource for long-term space missions and for supporting human life in space. The ease of access to these materials via Lagrange points is one of their most promising applications. Rather than expending vast amounts of energy and resources to travel to asteroids from Earth's surface, mining stations situated at Lagrange points could act as launching platforms, making it far easier to extract and process materials. By doing so, space industries would become more self-sustaining, reducing their reliance on Earth and making space exploration far more economically viable. But with this growing potential comes a host of challenges. While Lagrange points offer a kind of gravitational stability, they are far from easy to reach. The cost of transportation and the development of reliable space vehicles that can regularly travel to these points remain major hurdles. What this means for future space exploration is that more innovation in spacecraft technology is necessary before humanity can fully capitalize on these locations. Rockets must become cheaper, more efficient, and capable of withstanding long-duration missions. But perhaps one of the most exciting developments in this field is the ongoing work in reusable space launch systems. Companies like SpaceX are already making strides in reducing the cost of getting to space. Once this technology becomes fully operational, it could open the floodgates to much greater exploration of Lagrange points and beyond. Another fascinating angle to consider is the strategic importance of Lagrange points in terms of interplanetary communication. As our exploration of the solar system expands, maintaining communication with spacecraft and rovers on distant planets and moons becomes increasingly challenging. The vast distances involved create long delays, and the Earth's atmosphere and magnetic field can interfere with signals. In this context, Lagrange points may serve as vital relay stations that bridge the communication gap between Earth and our deep space missions. For example, NASA's Deep Space Network already serves a critical role in maintaining communication with spacecraft exploring the outer solar system. However, as humanity begins to send more frequent missions to Mars and beyond, Lagrange points could provide the perfect location for establishing a robust communication network that spans vast distances. By setting up relay stations at these points, scientists would be able to ensure that messages and data flow smoothly between Earth and distant space explorers, without the risk of signal interference. There is also potential for Lagrange points to serve as waypoints for future crewed missions to the outer planets. As humanity continues to consider missions to Mars, Jupiter's moons, and even beyond, the distance and duration of such missions will present enormous challenges in terms of both resources and logistics. In the future, Lagrange points could serve as refueling stations or points of resupply for long-duration space missions. Spacecraft could rendezvous with fuel depots or cargo ships at these points, replenishing their supplies before venturing farther into the solar system. These logistical hubs could make deep space travel far more feasible and sustainable. However, achieving this vision will require a complete rethinking of how we approach space travel. The technology for refueling spacecraft in space is still in its infancy. Current plans for refueling spacecraft usually involve carrying fuel with them or having to return to Earth for resupply. The idea of creating a network of refueling stations or even resource extraction points at Lagrange points could reduce this reliance on Earth-based resources and allow missions to become more autonomous. If we consider the scale of these operations, it's clear that developing the infrastructure for interplanetary travel will require international cooperation, innovation, and substantial investment in the necessary technology. As with any scientific or technological breakthrough, the development of Lagrange point infrastructure will likely be a gradual process. But the trajectory is clear. With advancements in propulsion systems, robotics, communication networks, and energy generation, humanity is slowly but surely moving toward a future where Lagrange points are no longer distant theoretical locations, but active hubs of space exploration, industry, and even settlement. One of the most exciting aspects of the future of Lagrange points is the possibility of creating permanent human outposts in space. While the International Space Station, ISS, has already demonstrated the feasibility of long-term human habitation in low Earth orbit, establishing permanent colonies at Lagrange points would mark a new chapter in humanity's spacefaring ambitions. These colonies could serve as stepping stones for deeper space exploration, offering safe havens for astronauts and scientists to live and work, all while minimizing the cost and complexity of space travel. In these outposts, we could imagine researchers working on experiments that are impossible to conduct on Earth, or engineers working on the next generation of space technologies. With a stable environment in these points, long-term space missions could become routine, allowing humanity to expand its presence in the solar system. This could be the starting point for a new age of space exploration, where Lagrange points play a central role in humanity's quest to explore not just our solar system, but the stars themselves. As we reach the final stages of understanding Lagrange points and their full potential, it becomes clear that these locations are not just theoretical curiosities. They represent the future of space exploration. Lagrange points offer more than just a convenient location for scientific instruments or mining operations. They could serve as the launch pads for humanity's next great leap into the cosmos. As we look toward the stars, these gravitational sweet spots stand as beacons of possibility, awaiting the day when we can truly harness their power and unlock the full potential of space exploration. The journey to this future won't be easy. It will require cooperation, vision, and most importantly, the continuous advancement of technology. But with the promise of Lagrange points offering stable bases for exploration, resource extraction, and even human habitation, the possibilities are limitless. The story of Lagrange points is one of untapped potential, waiting for us to venture into space and seize the opportunities that await beyond our planet. As we continue to explore the infinite possibilities of Lagrange points, one must consider the growing importance of these regions in the context of space colonization. The future of humanity may very well depend on our ability to harness the natural gravitational sweet spots in space for everything from research stations to full-fledged human colonies. As our exploration pushes beyond Earth's orbit, the strategic locations of Lagrange points provide not just stability for scientific endeavors but could also facilitate humanity's long-term survival. Lagrange points are ideal for any project that involves the long-term positioning of objects in space. One of the key advantages these points offer is their stability. Unlike orbiting directly around planets, which can involve constant course corrections due to gravitational disturbances, objects at Lagrange points can hover in place with minimal adjustments. This makes these points attractive for future space stations or research labs. A space station located at a Lagrange point would not require constant orbital corrections, reducing the fuel costs and maintenance required for keeping the station in position. For a future where we look to establish permanent presence in space, this offers enormous logistical benefits. Perhaps one of the most exciting applications of Lagrange points could be in the field of space tourism. With advancements in space travel technology, it's not beyond the realm of possibility that private companies could establish resorts or vacation spots in space, perhaps even located at a Lagrange point. Imagine a future where people can travel to space and stay in a luxury space hotel at one of these stable points. Not only would this be a massive leap for humanity's understanding of space, but it would also mark the beginning of a new era where space is accessible to everyone, not just astronauts, but ordinary people seeking to experience life in a microgravity environment. This potential is not purely speculative. Companies like SpaceX and Blue Origin are already developing reusable space vehicles and are actively working toward reducing the costs of space travel. These advancements, combined with the stable positions of Lagrange points, could transform the once distant dream of space tourism into a reality for future generations. As the commercial space industry expands, it is only a matter of time before these points become hubs for tourism, research, and commerce. However, such a future would require overcoming significant challenges. We would need to build spacecraft capable of regularly and efficiently reaching these points, and infrastructure would have to be created to support human life in space. While space tourism may seem like a far-off possibility, the groundwork for such a future is already being laid today. The potential for Lagrange points to be used as central locations for commercial, industrial, and scientific activities could serve as a stepping stone for humanity's more ambitious goals in space. As we envision these uses of Lagrange points, we must also turn our attention to the larger question of why humanity is looking to space in the first place. What motivates us to explore these distant regions of space? While it may be easy to get lost in the technological marvels and possibilities that come with Lagrange points, we must not forget the broader goals of space exploration, the search for knowledge, the desire to understand our place in the universe, and the hope that one day, we may be able to answer some of the most profound questions of existence. Lagrange points are not just places in space where objects can remain stationary. They represent a critical opportunity for expanding humanity's reach and opening up the cosmos to new possibilities. These points could offer the stability and convenience needed to establish footholds in space, whether for scientific exploration, industrial activities, or even the survival of humanity itself. In a sense, they are the stepping stones to the future of humanity's existence beyond Earth. But the full potential of Lagrange points won't be realized overnight. We are still in the early stages of understanding how to harness their power. While many space agencies and private companies are working hard to explore and utilize these locations, much more research and development will be needed before humanity can take full advantage of what these points have to offer. This includes developing technologies that can make traveling to these points affordable, efficient, and safe for astronauts and space tourists alike. It also requires the development of sustainable infrastructure that can support human habitation in space for extended periods. In the years ahead, as humanity builds on the knowledge we have gathered so far, Lagrange points will undoubtedly become even more important. They offer a range of possibilities that could drastically change the way we think about space exploration, travel, and even life itself. These gravitational sweet spots could serve as a crucial element in the expansion of human civilization into the cosmos, enabling new scientific discoveries, facilitating resource extraction, and creating new opportunities for humanity to thrive beyond the confines of Earth. For now, as we look up at the stars, the mysteries of space continue to captivate our imaginations. But with each passing year, we get closer to understanding and unlocking the potential of these distant regions. The future of space exploration will undoubtedly involve Lagrange points in ways we are only beginning to comprehend. They represent both a challenge and an opportunity, an invitation to reach for the stars and seize the countless possibilities that await us in the vast, unexplored expanse of space. In the long run, these points may hold the key to a future where humanity is no longer confined to the boundaries of Earth. As we look toward a future of interplanetary exploration and perhaps even colonization, the stability of Lagrange points could serve as our cosmic anchor, providing safe and reliable locations to support humanity's continued journey into the unknown. These gravitational sweet spots may one day become our bridges to the stars, guiding us toward a future that is as boundless as the universe itself. As with all great discoveries, the path to harnessing the power of Lagrange points will require vision, perseverance, and cooperation. But if we are able to unlock their full potential, the possibilities for humanity's future are limitless. And as we embark on this journey, we can look to the stars with a sense of wonder and anticipation, knowing that Lagrange points may hold the keys to a new era of exploration, discovery, and ultimately, the survival of humanity beyond Earth. As humanity continues to explore the vast expanse of space, one of the key advantages we have discovered is the strategic value of Lagrange points, not only for scientific endeavors but for resource management, technological advancements, and even the long-term sustainability of space exploration itself. These points, with their remarkable ability to balance the gravitational forces of celestial bodies, have the potential to serve as pivotal locations for future space missions. Their stable environment offers a golden opportunity for building infrastructure that could support humanity's future in space. Resource extraction is another critical area where Lagrange points could play a major role. In the near future, mining asteroids for valuable metals and minerals may become a viable enterprise. As we push toward the goal of establishing human colonies on Mars and beyond, the need for raw materials to construct habitats, spacecraft, and equipment will grow. Lagrange points could act as staging areas for these mining operations, as they allow spacecraft to park in a stable region of space while awaiting shipments or coordinating mining efforts on nearby asteroids or moons. In fact, as commercial space travel and mining expand, the logistical advantages of Lagrange points could make them indispensable to the success of these endeavors. Their stability would allow for more predictable operations, reducing the risk of encountering unexpected gravitational disturbances. Furthermore, these points could facilitate the safe transportation of materials and spacecraft, offering a consistent place to park resources and supplies as they make their way between Earth, the Moon, and Mars. Lagrange points could become the hubs where raw materials are gathered, refined, and distributed throughout the solar system, paving the way for a thriving interplanetary economy. Looking ahead, the use of Lagrange points may evolve as technology improves, allowing for more ambitious ventures into deep space. For instance, as we venture beyond our solar system, Lagrange points and other star systems could serve as vital staging posts for missions aimed at exploring exoplanets, or even interstellar space. While this may seem like a distant dream, the idea of expanding our reach into the stars becomes increasingly plausible as technology advances. The role of Lagrange points will be integral in these future expeditions, providing locations that are both stable and accessible to spacecraft on long journeys into the unknown. The importance of these regions in space cannot be overstated. Lagrange points represent more than just convenient locations for parking satellites or research stations. They are potentially the key to unlocking the future of human civilization in space. With their gravitational balance, they offer a unique environment where we can establish the infrastructure necessary to expand our presence beyond Earth's orbit. As space exploration continues to push forward, these gravitational sweet spots will become critical nodes in the web of human activity in space, providing the stability and strategic value needed to sustain long-term space missions. Of course, we must also consider the potential challenges that come with utilizing Lagrange points for human activities. Despite their stability, they are still locations in space where factors like cosmic radiation, solar winds, and micrometeoroid impacts can pose significant threats. Any infrastructure we establish at these points will need to be designed with these challenges in mind. For instance, future space stations or research facilities located at Lagrange points will require robust shielding to protect occupants from harmful radiation. Similarly, spacecraft that pass through or station themselves at these points will need to be equipped with the necessary technology to mitigate the impact of space debris or micrometeoroids. Space agencies and private space companies will need to invest heavily in developing the technology and strategies required to make Lagrange points viable long-term outposts. This includes everything from designing spacecraft that can withstand the harsh conditions of deep space to creating habitats that can protect astronauts from the dangers of radiation. Furthermore, as we develop the infrastructure needed to support human life in space, we must also consider the psychological and physiological effects of living in space for extended periods. Long-term exposure to microgravity, isolation, and confined spaces can have profound effects on the human body and mind. Ensuring that future space missions to Lagrange points are successful will require not just technological innovations, but also a deep understanding of the human experience in space. But despite these challenges, the potential rewards of utilizing Lagrange points for space exploration and colonization are immense. Imagine a future where humans can regularly travel to and from stable regions of space, where mining operations provide the raw materials needed for expanding our reach into the cosmos, and where scientific research can be conducted in environments free from the gravitational disturbances of planets and moons. Lagrange points may one day serve as the cornerstones of humanity's interstellar future, providing us with the infrastructure and stability needed to thrive beyond Earth. Moreover, the study of Lagrange points continues to yield valuable insights into the nature of gravity, celestial mechanics, and the fundamental forces that shape our universe. Scientists continue to explore these regions to better understand how objects interact within these delicate gravitational balances. The more we learn about the behavior of objects at Lagrange points, the better equipped we will be to utilize them in our future endeavors. This research is not only helping us develop the technologies needed to reach and settle at these points, but also deepening our understanding of the forces that govern the cosmos. As we look toward the future, the importance of Lagrange points will only grow. These stable gravitational regions offer more than just a place to park satellites. They represent the future of space exploration, resource management, and even human colonization. The possibilities are vast, and the potential is staggering. If humanity can unlock the full potential of these regions, Lagrange points may very well become the launch pads for the next great leap in human exploration. At the same time, we must remember that our journey into space is just beginning. Lagrange points are just one piece of the puzzle in our quest to understand and explore the cosmos. As we continue to push the boundaries of human knowledge and technology, we will undoubtedly discover even more remarkable phenomena and opportunities in the universe. And as we do, Lagrange points will likely serve as crucial stepping stones on the path to a future where humanity is no longer confined to Earth but instead extends its reach to the stars. In the end, the mysteries of Lagrange points are not just scientific curiosities, they are the keys to a future beyond our wildest imaginations. As we continue to study, explore, and ultimately harness these regions of space, we open the door to a new era of human exploration, one where the universe becomes our playground, and the possibilities are as infinite as the stars themselves. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.